Okay, so here's a video showing how to use double integrals to do the moment of inertia of a disk. So we're going to imagine, oops, I do want to leave myself a little more space, that we have our disk sitting here in the XY plane, and we're going to rotate it around the Z-axis with its center located right at the center of the Z-axis. Now we're going to think kind of in polar coordinates for this. So we're going to imagine our little dm has an arc length that is given by ds is r d theta, and then it is dr thick. And if we looked at that from the side or from above, I'm going to make that fully color, and then we're going to go small arc, come over, so this is r d theta. Back to the center, that's d theta, that's r, and dr thick. So dA, the area of a piece, is r dr d theta. Okay, same things kind of apply. This is mass m and radius r, so the density of the material is m over pi big R squared. And dm is going to be m over pi big R squared times the area of our little piece. We'll use our dA. All right, the distance to that piece is just r, so when we go to find I, we'll be going from r squared dm, we'll do our usual thing. All right, so outer integral is the theta, 0 to 2 pi. Inner integral is the r from 0 to the radius of the disk. Then we have r squared m over pi big R squared, which is a constant, r dr d theta. Okay, so m over pi big R squared, integral 0 to 2 pi, integral 0 to r of r cubed dr d theta. Execute the first integral. Pi r squared, we have r to the third, so we'll get r to the fourth over 4. And that will leave us with r to the fourth over 4 d theta. And then when we do the next part of the integral, we will just get r to the fourth over 4 can come out in front. We get integral from 0 to 2 pi of d theta. So theta between 0 and 2 pi, which is 2 pi. The pi can cancel, the 2 can cancel. Oops, one more thing. We can cancel this r squared and get an r squared on top. We get mr squared over 2. And you can see why I like this. It does make the setup for finding the moment of inertia of a disk pretty darn trivial. So you don't have to think about rings and adding the rings up or what the area of a ring would be. It is kind of handy. But, you know, you get the same result no matter how you do this. It works out the same way. If we'd executed, by the way, the d theta first, we would have recovered the equation for stacking rings. So try that for yourself, verify that it works. If you do the d theta integral first, everything else is constant with respect to theta, so you can just get the 2 pi, and you basically have the equation we had from when we did it in class. All right, that's going to be it for this one. Next up, I'm going to show you how to do the rectangular plate by double integrals. And oh, this one's nice.